Well, hello. Here we go again. I'm going to be talking about quantum phases in entropic dynamics. I will start by making a couple of comments about quantum mechanics. Then I will point out how the invited talk that I gave yesterday was wrong. Yes, and I'll fix it. And that's the whole subject here. Let's see what else we can learn from getting quantum mechanics right, or at least a little bit better than it was in the past. So here we go. Here is the problem with standard quantum mechanics. The problem is that quantum mechanics has a linear structure that's provided to you by Hilbert spaces. Wave functions form Hilbert spaces. And it has a probabilistic structure that's given to you by the Born rule. The magnitude of the wave function gives you probabilities. But there is a mismatch between the two. So let me start by mentioning quickly how that arises. Quantum mechanics is linear. That manifests itself in the fact that the Schrödinger equation is a linear equation. You can see here that the wave function only appears to the first power. So what that ends up meaning is that you have a superposition principle. If you have two solutions, then a linear combination of those two solutions is also a solution. And this seems trivial enough until you start talking about macroscopic objects such as the Schrödinger cat. Because if this guy here reflects a cat being alive, and that one is a cat being dead, then this is a cat in a zombie state that's undead. It's neither one nor the other. So that's cute. But this happens for absolutely the possibility of this happening is true for absolutely any macroscopic system, including detection devices. So there is a serious problem of measurement. The quantum measurement problem is one of the great challenges of standard quantum mechanics. Typically, if your detection device is undead in one of these zombie states, it can be in a superposition of having detected and not having detected. So when do these events of detection ever become definite? How do we ever get definite outcomes in a measurement? There are many solutions, and you can probably notice there that I put solution between quotes. Bohr's solution is to say, no, you have two realms, a classical and a quantum realm. Macroscopic objects belong to the classical realm, where quantum mechanics is presumably not supposed to apply. And then there is the macroscopic stuff. Another solution is for Neumann's solution, in which you say that not all processes in physics are equivalent to each other. There are two different modes of evolution of the wave function. One is the Schrödinger equation, another is what's called wave function collapse. There is the Everett solution, which says that collapse never really happens. Everything is always real, so you have a many worlds interpretation. There is the Bohmian solution, in which you have pilot waves guiding particles and doing all sorts of wacky stuff. So there are many attempts at solving this kind of problem, and the best evidence that none of these attempts is satisfactory is the existence of all the others. So here is the entropic dynamic solution, without quotes, because this is the really good one, all right? Which is that we take probabilities seriously. You see, the structure of quantum mechanics is that you start with a Hilbert space, that guarantees linearity, and then somehow you try to append a probabilistic interpretation on top of that, and these guys never live happily ever after. So entropic dynamics is an instance of entropic and Bayesian inference, as we saw yesterday. The entropic part is what leads you to the Schrödinger equation. The Bayesian part is what describes wave function collapse. So the wave function collapse in this language is just you apply Bayes' theorem when you do a measurement. That's all there is to it. And your probability distributions, of course, change rapidly with your measurement. Very good. But how are the variables for entropic dynamics and the constraints chosen? So, since I do not expect you to remember anything I said yesterday, I'm going to give you a very, very brief reminder of what it is that I was trying to cover. Particles in these models have definite positions. There are extra variables. There are some other variables there, y, and they are going to be described by a probability distribution, and their uncertainties depend on the position of the particles x. And really what enters the theory is the entropy of these y variables. The second important constraint, this is the first one here, that this enters. The second important constraint is that the motion is continuous. It can be analyzed in terms of short steps. And here is the distance. Let me see. This is the Pythagoras theorem. This is the distance. It's supposed to be very tiny. This kappa will at some point in the calculation be taken to 0. That helps me figure out, maximize an entropy, maximize the joint entropy of x and y to get a transition probability. Okay, very good. So this is basically what we had done last time. There is some kind of diffusive process that has a drift in the direction of increasing the entropy of these y variables. This piece here is the Lagrange multiplier that goes with that constraint. It's really, really interesting that in this theory, masses are interpreted as Lagrange multipliers. Very much like in statistical mechanics, in the maximum entropy approach, temperatures are associated to Lagrange multipliers. It's exactly the same idea. Very good. So next, let me see, next. There we go. Now you iterate that procedure many times and you get a Fokker-Planck equation. Then you impose energy conservation to update the constraints too. Entropic dynamics is this coupled evolution of probability distributions and constraints coupled to each other. So to get a so-called Hamilton-Jacobi equation, and here they are in the form of Hamilton's equations. This is Fokker-Planck. This is the Hamilton-Jacobi equation. It tells you how you update. This is going to become the phase of the wave function. And this equation here tells you how you update the entropy of the y variables. Very good. You combine this rho with this phi 0 into a wave function, something like that, and you get a Schrödinger equation. Very nice. So that's entropic dynamics in one shot. Okay? Now, this is really nice. I had said earlier that the linear, this is a linear equation, that the linear and the probabilistic structures of quantum mechanics were essentially mismatched. It doesn't seem to be the case here, does it? After all, I started from a purely inferential theory and I derived a linear equation. Yes, I derived a linear equation. This seems to imply that probability and linearity are perfectly compatible within the entropic dynamics approach. That's not true. And the interesting question is, wait a minute, but if it looks linear, and it is linear, what is the problem? So, this is an ED, an entropic dynamics that is probabilistic, linear, complex, but it disagrees with experiment. And that, of course, is the ultimate no-no. Here's the problem. The problem was originally pointed out in a different context. Now, of course, entropic dynamics had not yet been born in 1952. It was pointed out by Takahashi in 1952 and later rediscovered by Wallström in 1989. So what I'm going to describe here is called the Wallström objection. The idea is that if you have an entropic dynamics, oops, sorry. I'm going to start talking on the laser pointer and point. If you have an entropic dynamics of this type with a phase like that, it cannot describe non-zero angular momentum. Now, that's really bad. You need angular momentum. The whole reason quantum mechanics was invented was to describe the periodic table. The periodic table, you might remember, has columns and has rows and stuff like that. And all of those columns and rows have to do with S, P, D, F orbitals. That's angular momentum. And this theory cannot do it. It's linear, it's probabilistic, yeah, but hey, if you don't describe the periodic table, you might as well go home. The issue is that non-zero angular momentum, this is angular momentum, z component, comes quantized in units of h bar. Now, m here is not mass, this is just a magnetic quantum number, it's an integer. It's the standard notation. And a non-zero angular momentum requires a wave function that is exponential in some azimuthal angle. It's what tells the electron that it's supposed to be rotating. And what's the problem with this? It seems that this is precisely of this form. No, it's not. You see, when you go around 2 pi around the z-axis, this angle here increases by 2 pi. E to the I m 2 pi is 1. So the wave function itself is very nicely single valued. But the phase itself is multi-valued. If you go around in an angle, around an axis, you go from 0 to 2 pi, 4 pi, 6 pi. So at that point, the actual value of the phase is 0, 2 pi, 4 pi. It's a multi-valued function. On the other hand, if you look at the entropy that appears here, that's single-valued. You just go around, you come up to the same value. Rho is a density. Densities are necessarily single-valued. It's the probability of being there. So a wave function constructed in this way does not, well, it works. It provided me a Schrödinger equation, but this entropic dynamics is too restrictive. It doesn't describe everything I want to describe. It describes a subset of quantum mechanics. Now, whenever you do an entropic argument and you come up with a wrong answer, the issue is not, I've said this last time, but I have to repeat it. You do not discard arithmetic. You do not discard calculus. You also do not discard the laws of probability. You just recognize that you did not put enough relevant information into the problem. So what I'm going to do is I'm going to add more constraints. Now, at this point, you might be a little bit concerned that this guy is going to start adding constraints just to solve his problem. It's going to be an ad hoc addition of whatever you need to patch this solution. Actually, no. What I'm going to do is fix 2 problems. You might have noticed that in my talk yesterday, I never mentioned electromagnetic interactions. I never mentioned that the electron actually has a charge and it's pushed around by magnetic fields and electric fields. So my solution to this problem is say, no, my physics was incomplete. That was the theory was not working. Let me add electromagnetic interactions into the picture. This is very nice. Does that mean that angular momentum is somehow also connected to, might be. So we're going to add more physics into this problem. And more physics means more constraints. So what more constraints I'm going to add? I'm going to add an additional interaction to some extra fields, extra potentials. I'm going to invent a potential that, so it's a field at each point in this space, in 3-dimensional space, there is going to be, at x there is this potential, at x prime there is a potential, at any point there is, oops, no, I didn't want to get that far yet. At any point, there's going to be this field. Now, several things to notice about this field. First, the variables that I am introducing have the topology of an angle. If I go around by 2 pi, then the potential changes, increases by 2 pi. So this is where I'm introducing the multivaluedness of something to solve my problem. Second thing that you might notice, the 0 from which I measure the angles is different in different places. So what I'm saying here is that the 0 from which I measure these angles can be chosen independently in different places. That's what in physics is called a local gauge symmetry. So what I'm doing here is I am introducing electromagnetic interactions by introducing in the modern way. I'm introducing a local gauge symmetry. The theory has to be invariant under changes in the origin of these angles. I can go ahead and change them, and it shouldn't make any difference. Very well. But wait a minute. We have a little problem here. If you can change the origin of these angles arbitrarily, how can you tell that this angle here is the same as that angle there? How can you define derivatives? Oh yeah, okay, yes. If I were to do it right, I would also add, hey, not only these particles need to have angular momentum, not only they need to have electromagnetic charges, they better have spin also. I'm not going to do that today. So, local gauge symmetry. How can we say the angle here, the potential here, is the same as the potential there, when you can change the origins arbitrarily? This is the standard way. You introduce yet another potential, a vector potential called a connection. It's the thing that connects the values at one point and another. And the way this thing is defined is in such a way that if your angle is shifted by shifting the origins by a certain angle chi, which is position dependent, then the corresponding connection also changes by the gradient, which allows you to invent a corrected derivative. This is a gauge invariant, let me see, a gauge invariant derivative in which you take the regular gradient of this function and you correct it by the connection. You can see that if in this piece you add chi, and in this piece here you add the gradient of chi, the gradients cancel out, and so this is gauge invariant. So now I'm going to write down the constraint. The constraint is going to be a gauge invariant constraint that says the following. I want the component of the displacement along the direction of this corrected gauge invariant derivative to be some small quantity. So in addition to the previous, and this is, please notice that for each particle I have one of these potentials. The connection is the same for everybody, and there are n of them. So here we go. Maximize that entropy, subject to all three constraints: presence of y variables, the short steps, and now the gauge invariant constraint. And what we get is exactly what we had before: the entropy of the y variables, the short steps with the appropriate Lagrange multipliers, plus an extra piece that has the gauge invariant derivatives and the displacement, this is the constraint, multiplied by the appropriate Lagrange multipliers. So it's from now on, I just repeat what I did before. So you see how you can actually put more physics into entropic dynamics. Add the appropriate constraints. So you iterate over many short steps, you get a Fokker-Planck equation. If you impose energy conservation, that tells you how you can update at each step the presence of that entropy there. And so you reach eventually Hamilton's equations. Again, this is going to be the Fokker-Planck equation, and this is a kind of Hamilton-Jacobi equation. This tells you how rho, the probability, evolves in the presence of constraints, and this tells you how you update the constraints as rho evolves. So the Hamiltonian that one uses there is the Hamiltonian that one uses to derive the Fokker-Planck equation. Notice that there is a correction here. I'll talk about that in a second. And then there is an extra piece that is just exactly what we had before, includes scalar potentials, and it includes this other part that was coming from information geometry, that is a quantum potential. The phase of the wave function now, that phase that appears there, now is a little bit more complicated. It includes the entropy, it includes this diffusive part, and now it also includes those angle variables. Very good. I'm almost on time this time, yes. And the A bar that appears there is just a clever way of writing that monstrosity over there. Now, you combine rho and phi into a wave function, and you get a linear Schrödinger equation again, where now the derivatives of the Schrödinger equation have these corrections. This step is like really nice. I was talking just gauge symmetry, but if you compare with the standard notation, in the standard notation, this piece here is written like that, where these Q's are electric charges. So in entropic dynamics, charges are Lagrange multipliers, except for constants that take care of units and things like that. Charges are very inferential objects in this theory. So when you have a mystery about how it is, what is a charge? You take an electron and you sprinkle it with some fairy dust or something, and suddenly it gets attracted or repelled. What is it? It's a Lagrange multiplier. That's all it is. Weird. Electric charges are Lagrange multipliers. That's the first interesting result in all of this, except for the fact that I had a gauge invariant derivative there. That's an unusual one. Very good, but we still have a problem. The problem is still a mismatch between the linear and probabilistic structures. It disagrees now with experiment because this wave function violates the superposition principle again. Oops, the equation is linear. How can it do that? Well, the issue is that the wave functions now, I'll show this in a second, the wave functions are multivalued. So if you have two solutions that are multivalued, the solutions of entropic dynamics have to have the probability densities, the magnitudes, be single valued. A probability has to be single valued. You have to figure out precisely what you believe the values of these positions are. But because the equation is linear, the superposition is possible. It is a solution. It is multivalued because the psi 1 and psi 2 are. And therefore, in general, the superposition is going to be multivalued too, which means that psi 3 squared cannot be a probability. So you do have the linear structure, you do have a probabilistic structure, but they don't mesh at all. How do we solve that? I hadn't told you what the Lagrange multipliers were. I'm going to choose the constraints so that this works. So when we have something like a wave function like that and the phase like that, there is this piece here. I'm going to pick the Lagrange multipliers so as to solve the problem. I want this phi to be multivalued. The change in phi as I go around in a loop in which only one of the particles is being moved is given by an expression like that. If I remember that this guy is single valued, it doesn't contribute here. So I remain with just one of these angles. But this is an angle. This being an angle, it means that this object, this quantity, is 2 pi times an integer that depends on the loop. Now, if I want my phase to be, my wave functions to be single valued, I have to require that this guy here be an integer too. Here is an integer. So I am choosing the betas, the Lagrange multipliers, so this is an integer. That's nice. I've solved the problem of angular momentum here. It's multivalued. The wave function is single valued, but the phase is multivalued. But I just told you, and this is the main result of all of this, well, quite apart from solving the Polstrom objection, this guy here is charges. So what this is telling you is that electric charges are quantized in terms of a basic unit. This is an experimental result that I did not expect. All charges are multiples of the charges of the quark. The quarks have E/3 charges. And such a result is coming out here. And electric charges are quantized. And I did not need to use the standard arguments for charge quantization, which involves hypotheses that have not been verified by experiment. Either the existence of magnetic monopoles or the existence of grand unified theories. So this is very nice. It's a completely independent argument for quantization of electric charges. Conclusions. Entropic dynamics takes the epistemic view of the wave function to its logical extreme. Probabilities rule. The compatibility between the linear and probabilistic structures is achieved by introducing gauge symmetry. You're introducing physics. Electric charges are Lagrange multipliers. Electric charges are quantized. Thank you.